Hi everyone. So this is the second and final day of our asynchronous video instruction. Today I'm going to be talking about the dot product, which is a way of multiplying vectors. So that seems like a strange thing to be able to do. And this particular way of multiplying vectors is going to result in an object that comes out the other side that's not actually a vector. So we're going to be studying the dot product. And we'll be looking at three-dimensional and two-dimensional coordinate systems to do this. So the point of the dot product is that if I have two vectors, say A and B, and let's, for generality, we'll work in 3 dimensions here, although the same definitions are going to work in two dimensions as well. B1, B2, and B3. Then I guess I should put little hats over these guys so that we know they're vectors. It's not technically necessary, but at least when I'm writing here, it makes sense to do that, to distinguish between the vectors and scalars. The way that I dot these vectors together, or take their dot product, which we designate with a dot, is I write down the product of their first coordinates plus the product of their second coordinates plus the product of their third coordinates. So that's pretty easy to calculate usually. So for example, if I had the vector 1, 0, 1, and I dotted it with the vector 2, 1, 3, then I'm going to get 1 times 2 plus 0 times 1 plus 1 times 3, which is 5. And notice that the quantity 5 here, this is a scalar, which is a fancy word for number. And that's why sometimes this product is called the scalar product. So we say dot product, or we say scalar product because a number comes out. Or in another mathematical context, you may see this under the name inner product. And that's a name I can't really justify until you've seen some linear algebra, so we'll just leave it as dot or scalar product for now. So dot products give us a way to start looking at arithmetic involving vectors. So if we've got a way to add vectors, now we have a way to multiply vectors, and these things are going to interact with each other. That's, after all, that's what algebra is the interaction of addition and multiplication. So some of the rules here are covered in your textbook. I'll give a couple of examples of rules. One of the really interesting ones is this one. These are listed on page, the bottom of page 847 if you're interested. That the dot product of a vector with itself is equal to, well, if we have A1, A2, A3 dotted with itself, then because we multiply the terms by the similar term, first to first, second, third to third, and then add, we get A1 squared plus A2 squared plus A3 squared. And you should notice that that looks like the sum that is underneath the square root in the formula for the magnitude of a vector. And indeed, this is the magnitude of A squared. So there's an arithmetic trick here where I can use dot products to represent the length of a vector. That's frequently computationally useful. So I mentioned that one of the uses of this kind of multiplication is that you get this algebra, this arithmetic, where multiplication and addition interact with each other. Here's one way that could happen. So if you have a vector A and you dot it with a sum of vectors B and C, then it turns out to be the case that the dot product distributes. This is actually what justifies calling it a product. That this is equal to A dot B plus A dot C. So you end up with a distributive property. And you should check the rest of the properties here. I'm going to use them in example computations. I'll point out when I do it. There's just 5. I guess maybe I should, for the sake of completeness, I'll put the rest of them in. So property 2 is symmetry, which says that if you have two vectors and you dot them, it doesn't matter what order you do it in. Property 4 says that if you have a scalar, so if C is some scalar, not a vector, but a number, and you multiply it by A, and then you dot that with a vector B, then the C can just be popped out of the dot product. So this is some sort of associativity property. And then property 5 in the textbook gives is if you take the 0 vector and you dot it with anything, you get the 0 vector out. It's not surprising. So what do I mean by the 0 vector here? The 0 vector is the vector that has a 0 in each location. And it should be pretty obvious that if you take a bunch of zeros and multiply them by something, you get 0 out the other side. Okay. So the point of this is that the dot product induces pretty standard sort of arithmetic on vectors. Now the use of the dot product is twofold. The first we've already seen. The dot product encodes something about the length of a vector. So the dot product has two main uses. The first we've already seen, which is that the length of a vector A can be expressed as a dot product. And the second is that the dot product encodes the angle between two different vectors. Dot products encode angles. So what do I mean by that? I mean, if I have a vector A and a vector B, and I put the angle theta in between them, then it turns out to be the case that there's this really nice formula involving the dot product. So it turns out to be the case that using the law of cosines, you can show that A dotted with B is equal to the length of A times the length of B times the cosine of the angle between them. So this is a really useful formula in a lot of cases because oftentimes I want to know the angle that sits between two vectors. And the dot product is the primary tool for doing that. So there's proof of this in the text that you should walk through. It's very simple triangle geometry. I don't want to labor this video with that. I might show you guys in person. Let's compute an example. So I could say something like find the angle between, say, the vector about 1/2 root 3 over 2. That should look familiar to you. And 1, 0. So if we draw that picture, you can imagine on an xy plane that what we're looking at here is the vector 1/2 root 3 over 2 points up like this. And in this direction, we have the vector 1, 0. Now I've picked these because they're unit circle angles and I'm trying to illustrate the point here, but let's take a look and see what happens. So what the formula says is that the dot product of these two vectors, A dot B, should be equal to the length of A times the length of B times the cosine of the angle between them. Now, the dot product of these vectors is very easy to compute. It's 1/2. 1/2 root 3 over 2 dotted with 1, 0 is 1/2 times 1 plus root 3 over 2 times 0, which gets you 1/2. That's the easy part of the formula. I've picked these precisely because the length of this vector turns out to be 1, and the length of this vector also turns out to be 1. And so in the formula, what you end up with is A dot B, which we've already said is 1/2, is equal to the length of A, which was 1, times the length of B, which was 1, times the cosine of the angle between them. And then the cosine of theta is equal to 1/2 when theta is equal to pi over 3. So that's the angle between those two vectors. This is an illustration of how this formula works. A question you can ask is, when does this thing produce a 0? What does it mean? So let's take a look at what happens if we take two vectors that have the property that the angle between them is pi over 2. So suppose that you have sort of a right angle here. Suppose A and B have an angle of pi over 2 between them. So that picture looks like this. So right angle, pi over 2. If this is A and this is B, well, the formula says that then A dot B should be equal to the length of A times the length of B times the cosine of pi over 2. But the cosine of pi over 2 is 0. So this whole thing says that A dot B is 0. So when the angle is pi over 2, then the dot product is 0. And likewise, if the dot product is 0, and the vectors aren't 0, then the cosine of theta must be 0, which means that the angle must be pi over 2. So it turns out to be the case that the dot product also tells us when two angles sit at a right angle. So here's a definition. So we say that A and B are orthogonal. And a more common word you may have seen before for this is perpendicular. I think it turns out to be the case that one of the words has a root in Greek and one has a root in Latin, and we pretend that the concepts are different, but really they're pretty similar. So A and B are orthogonal if and only if A dot B is 0. So the dot product tells us when angles sit at, or when vectors sit at right angles to each other. So the last thing I want to talk about is the idea of a projection and the way that a dot product can tell us what that is. And so I'm going to talk about scalar projections and vector projections. The idea of projection is, this is an idea that you've used in physics before if you've taken a physics class and you've taken a work vector and you've decomposed it into perpendicular components, say a vector in the gravity direction and a vector in the normal direction. The idea here is that if you have a vector, say A, and you have a different vector, B, I might want to know how far down the shadow of the vector A gets on B if I sort of shined a light so that the shadow was perpendicular. So the light shines on A in a direction that's perpendicular to B. So if you imagine you've got a light up here, and the light is shining down on the vector, where would the shadow end? And the idea here is that this vector right here, we can think about that vector as the amount of the vector A that points in the direction B. So one way of thinking about this is the amount of A in the direction B. And it's a scalar. It's a number. That's what we mean by a scalar projection. So the scalar projection in some sense measures the length of the shadow, and the vector projection is a measure of the actual vector that points in that direction. So this vector here, this vector, the fancier name for this is the projection of A onto B. And because I've drawn it as an arrow, we can think about this as the vector projection. So the vector projection is the vector that's pointing in the same direction as B, but is the length of the shadow of A. And the way we compute all this stuff is we use the dot product to figure out what these things are. So it turns out to be the case that this is a formula that in some sense has to do with the fact that the cosine of this angle is involved. There's a bunch of geometry behind it. You don't actually need to know the geometry to remember the formulas. The way I think about it is like this. The length of A in the direction B, which is what we mean by the scalar projection, is given by the formula, I have no idea why they're using the word comp, but comp A onto B is the dot product of the two vectors, which in some sense captures the angle between them, and then we divide by the length of A. I have this backwards. This is B onto A. So basically what's going on here is we've made A into a unit vector, and then we've stretched B out with enough copies of A so that we pick up the correct direction. So the picture here is, here's B, here's A. If we take A and we divide it by its length, we end up with a little unit vector in the same direction as A. So this is A divided by the length of A, which is a unit vector, a vector of length 1. And then we just need to figure out how many copies of A we need to get all the way out to where the shadow of B falls. And so that's what this distance right here is. So if I take that and I dot A with B, then I end up with this length right here. That's the scalar projection of B onto A. Now if I take that scalar projection and I multiply it by a vector in the same direction as A, I'll get the vector projection. So the length of the projection is A dot B over the length of A, and the direction of the projection, just direction, so I don't care about length, so I'm going to use a unit vector. The direction is A divided by the length of A. And so if I want the whole vector projection, I write the projection now of B onto A is A dot B over the length of A times A over the length of A, or more concisely, sometimes you see this written as A dot B over the length of A squared times A. Okay, all of this stuff up here is a scalar, just some number, and then I take that scalar and I multiply it by a vector, and that gets me a vector. So the picture I want you to have in your head is that if you have an A and you have a B and you want to get down here where you're looking at this vector right here, let me erase this and reverse it so that we're doing the same direction that the theorem did. If this is B and this is A, and I want to know how much of B points in the direction of A, the way I compute that is I take the unit vector in the direction of A, and I multiply it by all of the length of the shadow, which is the dot of A and B over the length of A. This is the vector projection. So let's do an example of vector projections. So what does that look like? Doesn't look like anything because I turned off my pen. Example, find the projection of B onto A if B is equal to 1, 1, 2, A is equal to -2, 3, 1. So the pieces of this computation I'm going to need are the length of A and A dot B. So the length of A, in fact, I don't even really need the length of A. I need the length of A squared. If you remember the formula, the easiest way to remember the formula is the quantity I'm looking for is A dot B over the length of A squared times A. And the length of A squared, I have a formula for that. fact, the length of A squared is just A dot A. So the length of A squared is A dot A, which is 4 plus 9 plus 1, which is 14. A dot B is equal to, let's see, minus 2, 3, 1, dotted with 1, 1, 2. Negative 2 times 1 is negative 2, plus 3 times 1, which is 3, plus 1 times 2, which is 2, which gets me 3. Remember, all I did here was I did the minus 2 times the 1, and the 3 times this one, and the 1 times this 2, and then I add them together to get the dot product. So that means that the vector projection then, the projection of B onto A is A dot B, which was 3, divided by the length of A squared, which was 14, times the vector A, which was minus 2, 3, 1. And if you want to go one step further, you could write this as minus 3/7, 9/14, and 3/14. So that's a computation, example computation of a vector projection. And the most common application of this in early settings here is going to be in physics applications and the computation of work. But the idea of vector projection turns out to be one of the most important ideas in all kinds of approximation theory and in physics and various applications in engineering. So yeah, this isn't so hard. You are going to need to remember the projection formulas, and so I encourage you to do enough exercises with these that you're completely comfortable with these vector computations. All right, so I'm looking forward to seeing you guys on Tuesday and being done with this. So I'll see you soon. Take care.